Welcome to Grade 12 Artificial Intelligence. In this module, you take the wheel. Instead of following a worked example, you'll plan and run an AI project of your own, from a first question all the way to a result you can stand behind. This is the step that turns someone who uses AI into someone who investigates with it. Here is our plan for the lesson. We'll first ask what independent research really means. Then you'll choose a question and read what is already known about it. You'll plan a method and gather your data ethically. You'll build a model and evaluate it rigorously, then analyze the results and state their limitations honestly. And finally, you'll communicate the work so that others can reproduce it. Let's begin with what independent research is. It is not repeating a tutorial where the answer is already known. It is a project that you direct yourself from a question nobody has answered for you to a result you produce and defend. Your project runs along a single timeline through 6 milestones. First, a question worth answering, then a review of what is already known, then a method with data gathered ethically, then you build and rigorously evaluate, then you analyze stating the limits, and finally you communicate it so others can repeat it. The timeline moves forward, but it is not rigid. A finding can send you back to refine an earlier stage. Let's walk these milestones one at a time. Everything rests on the question you choose first. A strong research question is specific, answerable, and measurable. Asking whether a model can tell healthy maize leaves from diseased ones is sharp. Asking whether AI helps farmers is not. Keep the scope small enough to finish in the time you have, because depth beats breadth in a student project. Before you commit, check that the data you'll need actually exists and that you can obtain it. Then review the literature. Read the papers, data sets, and existing models in your area to learn what is already known. Find the gap your project can fill and cite the work you build on rather than rediscovering it. With a clear question, you can plan how to answer it. Next, decide how you'll answer the question and write that method down before you collect anything. Plan how the data will be split, most for training, a slice for validation, and a held-out slice for the final test. Choose a baseline, a simple, honest reference, so you know what beating it would actually mean. Now the part that matters just as much, ethics. Use only data you have permission to use, with consent where people are involved, and protect their privacy. And watch for bias. Ask whether your data fairly represents everyone the model will affect, because a model learns the bias in the data you feed it. With an ethical plan in place, you can build. Now you build the model and evaluate it rigorously. Take a project that classifies maize leaves as healthy or diseased. Split the data once into training, validation, and a held-out test set, and keep that split fixed. Tune and choose your model on the validation set only, and never touch the test set while developing. Compare against a baseline, always guessing the most common class scores 60% while your model reaches 89. But one run is not evidence. Repeat the experiment over several random seeds and report the average with its spread. Report a confidence interval, a range the true value likely sits in rather than a single lucky number. Now you have a result worth analyzing. Once you have numbers, analyze them honestly. First ask whether the gain is real. A significance check tells you the difference is unlikely to be chance, not just one lucky run. Then ask whether it is meaningful, because a tiny improvement can be significant yet too small to matter in practice. Look closely at the errors. Which cases does the model get wrong, and is there a pattern? State the limitations plainly. Maybe your data was small, from one region, or gathered under narrow conditions. And remember that a negative or mixed result is still a real finding. Reporting it honestly is part of good research. The last step is to share what you found. Finally, you communicate the work. Write a report that states the question, the method, the results, and the limitations, so a reader can follow and judge it without you in the room. Make it reproducible. Release your code and the data or clear instructions for obtaining it. Fix and report your random seeds and the versions of the libraries and models you used, so the same run gives the same numbers. Show exactly how you evaluated so a reader can check the claim for themselves. Reproducibility checklists used at major venues ask for just this: code, data, settings, and statistics, and cite every source honestly, with no fabricated or copied work. That honesty is what makes your finding count. Independent projects look different around the world, but the process is the same. In Rwanda, a student might build a crop disease classifier from leaf photographs or a Kinyarwanda text helper that suggests the next word. In the United Kingdom, a student might predict a city's air quality from weather and traffic data. In the United States, another might forecast basketball outcomes from match statistics. Different questions, but each one needs real data, a baseline to beat, and testing on data the model has never seen. And each can have local impact. A small, honest project can still genuinely help the community around you. A few traps sink even promising projects, so let's name them. First, scope set too wide. Choose one question and go deep, rather than skimming many. Second, data leakage, tuning on or peeking at the test set, which secretly inflates your score. Third, reporting a big number with no baseline. Without a reference, the number means nothing. Fourth, claiming success from a single lucky run instead of averaging over several. And fifth, hiding your limitations or using data you had no permission to use. Avoid these five, and your project will hold up to scrutiny. Let's gather the key ideas. Independent research is a project you direct yourself, from a question all the way to a report. Choose a specific answerable question with data you can actually obtain. Write your method first and gather data ethically. Split the data once, compare against a baseline, and repeat over several seeds. Analyze honestly, state your limitations, and report results even when they are negative. And make the work reproducible with code, data, seeds, versions, and citations. Now let's check these ideas with 3 quick questions. Here is the first question, which is the stronger research question for a student project. Is AI useful for farming, or can a model classify maize leaves as healthy or diseased? The first is vague, with no clear way to answer it. The second is specific and measurable, and you can gather the data to test it. A good question is narrow enough to actually answer. Question 2. You want to use people's photographs to train your model. What must you check before you do? You can only use data you are permitted to use. That means getting consent from the people involved and protecting their privacy. Ethics comes before accuracy. Last question, and it brings our ideas together. Your model scores 89% on one run, and a classmate says that proves it works. What is missing? A single number proves very little. You need a baseline to compare against, so you know what beating it means. And you need to repeat the run over several seeds to show the result is not just luck. Only then is the claim trustworthy. Wonderful work. You now know how an independent AI project moves, from choosing a sharp question and reviewing the literature through an ethical method and a rigorous evaluation to an honest, reproducible report. Choose a question that genuinely interests you, keep its scope tight, and treat your data and your results with honesty. Do that, and you are no longer only learning AI, you are doing research with it. I'll see you in your next module.